All right. So my name is Antoine Chevrot. I am an ex-Onera from Toulouse. So I've done this work mostly while I was still working at the Onera with my colleague Luis, who is a little bit too far from here to come today. Sorry for him. So we worked for the past few months on trying to assess the authenticity of fuel consumption calculation, mostly based on open data. So this is what I'm going to be presenting today. No. Okay, I'll click once. Okay, so I'll give a quick introduction on the topic, present the method that we used, and present the different results that we had on the different performance models, and we'll discuss and conclude on those results. So as an introduction, so lately that has been, and it has been presented before for obvious reasons, there has been many incentives to calculate the CO2 emissions of the aviation. You can find a lot of work in the literatures, and there are some discrepancies depending on the method used and depending on several input variables that are used for the calculation of it. So it ranges it ranges from 8, so it's only for passenger aviation, and for this year it was 2018 only. So you can see that there are some discrepancies. Seymour and Jansi they had the similar approaches. They used the FIT method, which is a method presented by Seymour, and they managed to get very similar results, even though they didn't use the same data. And there are different data on that. So the idea is that there are many variables and many different hypotheses taken to calculate and that are impacting this calculation. So we wanted to try to evaluate the impact on those different hypotheses on the calculation of the fuel consumption. So the method that we used is that we tried to get from OpenSky real-life example of trajectories. So mostly it was pair airports. And from that, we extract information from the OpenAP kinematic model that was called RAP before, I guess, I think. And from that, we get the flight envelopes. It was presented just before in the presentation before. Different variables, just like, for example, the speed during climbing, the height of the cruise, the altitude of cruising is all probability distribution in the kinematic model. So we use that to generate a first draft of the different trajectories. We needed a lot for the simulation and for the Monte Carlo simulation. This first draft was used to have a first estimate of the fuel that was needed to fly this flight. And we use this first fuel estimate to calculate the takeoff weight of the flight. This takeoff weight was, so there was the fuel, there was the weight of the passengers, and there is this whole calculation for that. We can talk about it later. From this takeoff weight that I called payload here, we did a second generation, still using OpenAP, but which is supposed to be more precise because we are supposed to be using a little bit better takeoff weight. On the first generation, I think that's probably what Maximilian used. There is this 70% of the maximum takeoff weight that is used for which is the default weight for the generation. And from that, we use the model to calculate the fuel flow on this trajectory. And those different inputs used with the estimated fuel flow was used afterwards to do this Sobel's experiment. And we use the OpenTerms library to calculate the Sobel indices. So here are the different scenarios that we generated for this study on OpenAP. So there are 4 different flights. There is one from Toulouse to Amsterdam, which is supposed to represent a relatively short flight. Then again, the airport pairs here are just for the idea of the length of the flight. These are the ones that we found on OpenSky, and then we generated them afterwards. And the last was London, Washington DC, which is supposed to be the bigger route at the end. All right, I don't know if it's well visible. Okay, no, it is okay. So here are the several variables that we considered for this experiment. Of course, we can discuss later, like different other variables that can be introduced. There are so many of them, but it's complicated. We have to limit a little bit. So there is this average weight per person. So on several studies that I talked beforehand, they use the ICAO report that says that, I didn't put kilograms, but it's 100 kilograms on average per passenger. So instead, we used a normal distribution that is so centered on 100 kilos with a minimum of, I think it was 60 or 80 kilos and a maximum of 140 or 150, something like that, to limit a little bit the weight per person. The other main contribution for the takeoff weight is the aircraft load factor. On the IATA reports on 2019, the average was a little bit less than 82% for the passenger aircraft. We also used the range deviation. So you saw just before the range of the flights that we generated, and we added a 5% deviation from the original trajectory. So sometimes it was, I mean, it's more or less 5%. So this is supposed to recreate some modification of the trajectory that is made, for example, for a meteorological reason. So we wanted to check if this range deviation would have a huge impact compared to the others on the fuel consumption. There is this cruising altitude, which is taken from OpenAP. The descent thrust. So this is also from OpenAP. If I remember properly, OpenAP is using this thrust factor to calculate the fuel used during descent. 0 being a descent without any thrust, and 1 being using the max thrust. And I think that the numbers here are between 0.3 and 0.4, if I'm not mistaken. I mean, it can be less, but it's maximum 0.4. And lastly, so from the presentation before as well, there are different schedule speed that are taken in the 3 different flight phases. So there is the max speed during cruising, there is the CAS speed that is used during takeoff, not takeoff, but during climbing and descent as well. And we wanted to check if those different input could have a huge impact on the fuel estimation at the end. So for this analysis, we use the variance-based sensitivity analysis, so which is also called Sobol's experiment on most of the case. So the idea is to decompose the variance of the output of the model into fraction, which can be attributed to the different inputs. So these fractions that are called Sobol indices are can be added together and always result to 1. So for example, if you have the Sobol indices of 0.6, that means that this input account for more or less like 60%. You can see this of the final variance of the model. So there are 2 orders. So there is what we used for this. There is this the first order index and the total order index. The first order measure the effect of varying the variable alone by itself, which is then averaged over the variation of the whole model. And then there is the total order, which is not only the variance of the input, but also the variance caused by interactions on the other variables with them. And then it's also average over the variation of the model. So here are the first results that we got on the Sobol indices using OpenAP. So here we have the two results for both the A321 and the A320 on the 2,300 kilometers flight. So as you can see, there are three main parameters that are, let's say, accounting for most of the fuel estimation consumption, which is the average weight per person, the cruise altitude, and the load factor. What's interesting here, and that's why I put them next to each other, is that, again, it's using OpenAP, so there might be some discrepancies with reality. So we can see that using the default engine for both A320 and A321, the Sobol indices are quite close to each other, meaning that, yeah, the impact of those three parameters are similar on both models of aircraft. So it changed. Here are the two other scenarios that we decided to check. The first one is on the shorter flights, and the one on the right, yes, is the one for the B77 777. So here, which is quite surprising, using OpenAP, we can see that the cruise altitude, even for a short flight compared to the one on the 2,300 kilometers, the cruise altitude is way more impactful than the variables that are taking for the takeoff weight. I think that it's way more understandable for the longer flight, as the cruise is longer, so the modification of the cruiser altitude makes more sense to be the most incompatible. So here, since we mostly used OpenAP for our first experiments, we wanted to use another model to try to limit biases from using a single model, to check if we were having more or less similar results using another model. We have to be, I mean, the OpenAP and BADA that we used are calculating the fuel flow a little bit differently. They don't have the same equations. So this is also interesting to see if using different ways of calculation for the fuel flow, we managed to get more or less the same sensitivity, sorry. But we have a problem. So the BADA experiment is not open sourced due to licensing. So we are not sharing all the data that we got from that. And we're not really doing any comparison. We are just showing by using, you know, different. So this is the XX and YY aircrafts. We couldn't put A and B because that would have been too obvious. So the first one is on an 800-kilometer flight, and the other one is on a 6,000-kilometer flight. And on the 800-kilometer flight, we can see that using BADA, the average person weight and the load factor are supposedly the ones that are the most impactful, while for a longer flight, we again find that the cruising altitude is the one that is the most impactful. Which, when I put them next to each other, so that's not a comparison, I'm just happening to put them next to each other, makes sense. We can find that there are similarities in the Sobol indices on the cruising altitude, with a little impact of the load factor. And here it's the same, so it's not exactly the same distance, but the idea is similar. And that's why I was telling you earlier that there is this little discrepancy. So that would be interesting to discuss with Janzi, that why using a short range flight on a A320, we get such a huge impact on the cruise altitude. I used this range, so 580 kilometers, but also got the same results on the 300 kilometers or a 400-kilometer range. So maybe there is, you know, a lot of impact on the on the A320 for the short distance. So what's interesting with this study is that we can use it for a lot of different things. From the different talk that we had today, I think that we could include the sensitivity of having go around and check if this has a huge impact compared to other things that we have here. In this instance, for example, we try to fix the payload and the altitude. So the idea behind fixing the altitude is that the intent of the cruising altitude is often known. So that's an idea to just fix the altitude, to know that. And we fixed the payload because it had such a huge impact on the sensitivity that we wanted to check if, other than the altitude and the takeoff weight, which other parameters had the most impact. And in this case, it was the range deviation and the Mach during climbing. Other usage of what we have done is we can eventually compare the fuel consumption between two mission sizes. So here on the axis, we have the load factor, and on the Y, we have the consumption in liters of kerosene for 100 APK. So that can tell us, well, that obviously when you are doing a longer flight, you per person for 100 kilometers, you consume a little bit less. So those results can be also added. We have other small results like that I didn't show today because of lack of time. So we can discuss, there are a lot of limitation of this approach. There are a lot of discussion. So the impact of the cruise altitude, one of the main ways to avoid contrail is by leveraging the cruise altitude. So it would be interesting to check the CO2 impact and the non-CO2 impact to see, because on the long range flights, we saw that the cruise altitude had the most impact on the CO2, I mean the fuel consumption, but also the CO2 emission. So we would be interesting to check the pluses and the minuses between avoiding contrails and changing the cruise altitude. As I say, we have a surprising impact on the cruise altitude on short flights using OpenAP. So this would have been this would be interesting to check out why exactly. We had some problem with the efficiency of the Monte Carlo simulation for sensitivity analysis. So as I explained, we had two trajectory generation, which can be quite long already, and to have enough data to perform the method we needed at least 2,000 experiments. Even 2,000 was limited, as you saw. There was a big variance already on the indices. To limit this problem, we only generated 1 point every minute for the trajectories. So this could maybe be improved. And also the other problem is that for these kind of methods, we need to assume that the different variables used are independent, which they are not, clearly. For example, the speed during cruising and the altitude during cruising are correlated quite heavily. And in this method, we couldn't really correlate them easily. And the last point is the accuracy of the performance model. So it's adding its own set of uncertainty that would need to be checked by the equation that they are using compared to the reality, for example. And some data are not always available in open data. For example, the engine used. In this approach, we use the default engine that was given by OpenAP. So to conclude, we managed to create a complete open software package to evaluate uncertainties and apply a sensitivity analysis to the fuel consumption calculations. So this work is an initial exploration of the input usable for sensitivity analysis. As I said, and as we saw beforehand, we can use a plethora of different variables to calculate the fuel consumption. And depending on the model that we use, some model will be able to introduce those variables, some are not. So this would have to be explored, which one would be the most interesting. The cruising altitude and the takeoff weights are the main contributing factors to the fuel consumption in this study. This would have to be confirmed, but from all the ones that we have seen, this would be the case. It confirmed the results that are found by Seymour and all with their FEAT approach, but we only used open data. For example, them used the OAG dataset to use on the whole world. The Python the Python code is available on GitHub, but for now there's not even a README. I have to add the README to tell you exactly how to use it. But this works. I already put the data sets and the different figures that I got, and it's quite straightforward to install, so there shouldn't be any problem. For future work, so it would be interesting to compare our model and our method using other sensitivity analysis. There are a lot of them on OpenTerms, and that would be interesting to check other. We could use the uncertainty propagation to calculate the aviation fuel consumption worldwide to check if what we get is more or less in the same area than the other methods that we got. Of course, this is complicated because a lot of uncertainties are evening out depending on, for example, if you fly over the Atlantic. It would be interesting also to find some way to use more directly data feeds from OpenSky Network, because for now we are depending heavily on the generation of OpenAP due to the forced interpolation of the ocean, for example. We would love to be more exhaustive in our input set. So it would be interesting to add the age of the engine, the type of fuel that is used to modify the takeoff weights, etc., etc. I mean, the world is your limit. I mean, we've seen so many different presentations that could use this uncertainty analysis. And finally, I would have to find a co-author with good knowledge on sensitivity analysis. So if there is anyone in here, that would be very appreciated, because that was quite new for me and my co-writer. So that was quite a challenge to use, but I think that this could be a nice contribution to our community. We thank you, and do you have any question?
Yeah. Thank you, Antoine. So we are ready to take the questions.
Thank you and congratulations for your work. I think for me was really interesting. My question is, did you have the chance or have plans to calibrate your fuel consumption data, or in particular a takeoff weight, with any actual data?
That would be nice to do that. The thing is that the takeoff weight is very complicated to really well estimate, because for now, right now, we only use for the payload, we only use the passenger weight depending on the number of seats that are available in one flight. But there are a lot of companies that are using extra freight to complete when there are not enough during the load factor. So that's already a big modification for this experiment. Of course, that would be nice. Even a small set would be allowing us to confirm a little bit more of the approach.
That's the point, because otherwise you are progressing, and you're progressing in a very nice direction, I'd say. But you are aiming to perform a sensitivity analysis on something that is purely a model with a lot of assumptions.
Yes,
in the middle.
exactly.
So
yes.
If you could secure some of these intermediate steps.
I know, I agree.
Nice. Okay.
I agree. That's why we use this data approach to at least check if, because only doing this with OpenAP wouldn't have been a sensitivity analysis on the fuel consumption. It would have been a sensitivity analysis on OpenAP.
Okay.
But here we at least we have some confirmation with another model. But yeah, there are still a lot of using real data on everything would be way better. I agree.
Thank you. I particularly found very interesting the takeoff weight estimation. So
yeah. Well, yeah, especially since it seems to have such a big impact on on the estimation. Yes, thanks.
Thank you. Next question.
Hi, thanks a lot for your presentation. Because you do not have independence of your input, I wouldn't be very confident in the decomposition of the variance with the Sobol index. So I was wondering, have you tried Shapley indices instead?
No, not yet. This is one of the things that we want to try out. The independence is a problem, especially on the and I think this is mostly one of the problem with this altitude, which is like not supposed to be that high for these short flights. I would say again, that's the same idea. Maybe it's not that accurate, but at least having from different models, it gives us some kind of security on the fact that we have at least a little bit of truth in what we are getting. But yes, we need to address this dependence problem between the different variables, because obviously this is a big thing in this case, in this study. Yes.
Thanks.
Thank you, Antoine, for the nice presentation. I'm sure that you know where's my question is going now. It's about this altitude. Can you elaborate a little bit more on how you, which altitude you use for the bottom model? Is it the same altitude, or is
Yes, that's the thing. And I think this is, I mean, I know already the problem. I just didn't elaborate here. But the thing is that so just stop me if I'm mistaken, because you've done that. But the idea of the altitude that is the optimal altitude for the flight, and it's been calculated through real data. And I'm sure that, of course, short range flights are not optimal. And this is the reason why I'm sure that in the 2000 trajectories that I simulated, there are a lot of flights that are going above 1100 meters, which is never happening for such a short flight.
Yeah. So my impression is that if you generate a trajectory based on this kinematic model from OpenB, you are basically reproducing the flights that happen in real life. And the flights happening in real life, they are, for short ranges, they're really optimal. So they don't climb to the optimal altitude.
Yeah.
So they kept their relatively low altitude.
Yeah.
And then they basically consume a bit more fuel in general.
Yeah.
But if you have the same input to the OpenAP and to BADA, and then for BADA you have less significance, right?
Yeah.
Is that what I
Yeah, that's what I had. Yeah.
Okay.
So that means that there is another problem somewhere as well.
Yeah. So the OpenAP, I know the way you calculate the view flow, that you consider both altitude and speed.
Yep.
But for BADA, I think
no, they don't use only that.
Only one of the altitude, right?
Yeah.
Yeah. So that could explain some of the reasons
Possible.
there.
Yeah.
But why that not applied to the longer flights? Then is another mystery. So
there are ways to explore, especially that I used the last beta version, and the trajectory generation is completely different than from the previous one. So there might be some changes as well on that.
You just mentioned trajectory generation. So do you use different trajectory generation method
For
BADA and OpenAP?
BADA has its own.
Oh, so you are generating trajectory using the BADA.
Yes.
Okay. So I think in that case, the comparison can also be offset, because the way that how the trajectory are generated. So what I would recommend is that you have
use the same trajectory.
Yeah, because essentially, if you're validating, if the model produce consistent results, and I think the input should be at least similar.
Well, that's not very complicated. That's that's the good thing, let's say. Yeah.
And my second question, also kind of comment, is that I don't know if I share with you, but there's a new library called OpenAP Polymer. It's basically a reduced order like library based on the OpenAP, because OpenAP have to give the like a mass, and then you have to basically using the optimizer to generate optimal trajectory, and then it's the best way. So what we did is we simplified the model. So if you give the weight, and I also believe there's a distance,
Oh yeah,
it
this
gives
is
you
the thing you told me about.
it
Yes,
gives you
yes,
the
yes.
most optimal trajectory
Yeah.
and also most optimal fuel flow for that.
To get that directly. Yeah,
yeah,
that
so
would
you
be
would-
maybe easier for the generation and
in fact, essentially that it has already be generated because when we
true.
calculate this,
Yeah, you get
this spread,
directly the yeah.
So maybe you can also try to reference using that to compare with the BADA to see.
Yeah, that's
what
so
will
to
be the
have another one.
discrepancy.
Yeah, that would be
Yeah.
interesting.
I
Yeah,
do
I could-
believe that BADA, when it generates, you try to use more optimal trajectory, right? So if
possibly
you
yes.
compare this one with the polymer output, then you might have a better
Yeah,
alignment.
but this would be nice to add this third option. I wanted to also to add the feet because it's the same with the range distance and the
Correct.
type of aircraft. You can directly get the fuel flow, so that would be interesting. Also, it's just that then you can't really add variables to it to.
Yeah, and also if you use polymer, that's the minimum fuel flow. So
Yeah.
it's always optimal
Yeah.
trajectory. Then
Yeah,
on top
exactly.
of cost index, and you can redo the simulation with different cost index.
Yeah.
But we'll be fine. Thank you.
Thank you.